All right, so yeah, welcome everyone. Thank you for joining our department seminar. So today is my great pleasure to have Dr. Vardi to join us remotely and give a talk on proof of generalization in over parameterized neural networks. So Gal, he is currently a postdoc co-hosted by Professor Nati Srivara and Amit Daniali at the TTIC and the Hebrew University as a part of the NSF and Simon's collaboration on the theoretical foundation of deep learning. And prior to that, Gal, he did another postdoc at Wisman Institute hosted by Ohad Shamir, and he received his PhD from the Hebrew University, advised by Ona Kupferman. Okay, so if you work in the area of deep learning theory, you must have read many great work by Gal Vardi. So he has done many interesting and important work about the implicit regularization or binary fitting and many other things in the area of deep learning theory. Okay, so with that, please join me in welcome Gal, and the floor is yours, Gal. Yeah, you can go ahead when you are ready.
Thank you. Thank you very much. It's a pleasure to be here. Thank you for the invitation. And in this talk, I will discuss provable generalization in overparameterized neural networks. So neural networks are often overparameterized, which means that the number of parameters in the network might be larger than the number of examples in the training data set. And in such cases, there are usually many different solutions that fit the training data set. Namely, there might be many different neural networks that interpolate the training data, but from this large set of possible solutions, it seems that from this large set of possible solutions, some of the solutions also generalize well on test data, and other solutions only overfit the training data and do not generalize well. But empirically, it seems that gradient methods tend to converge to solutions that generalize well. So it seems that there is some kind of implicit bias towards the good solutions, the solutions that generalize well. And understanding this implicit bias is an important question in the theory of deep learning, and it has been extensively studied in recent years. And it is believed that understanding implicit bias is a key for understanding generalization in deep learning. And indeed, in this talk, we will discuss 3 recent works that consider implications of the implicit bias, and we will focus on generalization. In the first work, we will consider generalization in univariate ReLU networks. It is a joint work with Itai Safran and Jason Lee. Then we will consider generalization and adversarial robustness in ReLU network trained on clustered data. It is a joint work with Spencer Frey, Peter Bartlett, and Nati Srivara. And the third part of this talk is also about a work with the same authors, and it is about benign overfitting in leaky ReLU networks and linear classifiers. So as I said, the implicit bias has been extensively studied in recent years, and there are many different results for different settings. And in this talk, I will just focus on one setting. We will focus on the case where we have fully connected ReLU or leaky ReLU networks. We denote here the network by phi theta x, where theta is the parameters and x is the input. We will consider training the network using gradient flow, which corresponds to gradient descent with an infinitesimally small step size. It can be viewed as an approximation of gradient descent. And we will consider binary classification. So the labels will always be in ±1. And we will train the network using, with respect to the logistic loss. Now, we also need some simple definitions in order to introduce our setting. We said that the network is homogeneous with respect to the parameters if changing the scale of the parameters is equivalent to changing the scale of the output. Namely, if we multiply the parameter theta by some positive alpha, then it is equivalent to multiplying the output of the network by alpha to the L for some constant L. Now, for this talk, the important thing to know about the definition of homogeneous neural networks is that this definition holds in two-layer networks. And in this talk, we will focus on two-layer networks. So the networks that we will talk about today are homogeneous. And note that even if we have bias terms in the hidden layer, the network is still homogeneous because we consider homogeneous networks with respect to the parameters. So if we add bias terms, the network will not be homogeneous with respect to the input, but it will still be homogeneous with respect to the parameters. Okay, also, we say that gradient flow converges in direction to some parameters theta tilde if, as the time t goes to infinity, the parameters, the direction of the parameters converges to the direction of theta tilde. Now, since we train the networks using the logistic loss, and the logistic loss does not get value of exactly 0, it is strictly positive. So it means that if the logistic loss converges to 0 loss, then the norm of the parameters goes to infinity. Because the only way to reach training loss that approaches 0 is to have parameters where the norm of the parameters goes to infinity. So typically, when we train networks, as the time goes to infinity, the norm of the parameters will go to infinity. But since we consider homogeneous networks, we will mostly care about the direction of the parameters and not about the size, the scale of the parameters. And in this talk, we will use the following theorem, which was shown by Liu and Li and G and Tilgarsky. They showed that in homogeneous networks, if gradient flow reaches some sufficiently small training loss, then it converges in direction to a KKT point of the max margin problem. The max margin problem is the problem of minimizing the norm of the parameters, subject to having a margin of at least 1 for all training examples. So we need for every training example xi, we need the network to classify xi correctly, and the absolute value of the output needs to be at least 1, and we want to do it with the minimal norm of the parameter. Now, the theorem guarantees convergence to a KKT point of this optimization problem. The KKT point is an extension of Lagrange multipliers. Since in Lagrange multipliers, we can only have equality constraints, and in the KKT framework, we can also have inequalities. And the formal definition of a KKT point is a point that satisfies a set of conditions called KKT conditions. These conditions are given by these equations that are given here. And for this point at the talk, we don't really need to talk about the details of these equations. For now, what we need to understand is that the theorem by Liu Li and G and Tilgarsky guarantees that gradient flow will converge in direction to a network that satisfies this set of equations. Now, these KKT conditions are known to be necessary but not sufficient for optimality. It means that it is possible that gradient flow will converge to a KKT point, but this KKT point might not be an actual optimum of this problem. So gradient flow is not guaranteed to actually maximize the margin. It is only guaranteed to converge to a stationary point of the margin maximization problem, KKT point, which is a stationary point of this optimization problem. So we're not guaranteed to maximize the margin, but intuitively we can think about this theorem as saying that there is kind of tendency towards margin maximization, although we're not always guaranteed to maximize the margin. So given this known result about the implicit bias of gradient flow in homogeneous networks, the natural question is, how can we obtain implications of the implicit bias? And we can think about three possible approaches to obtain implications of the implicit bias. One approach would be to assume that gradient flow actually maximizes the margin, that it converges to a global optimum of this optimization problem. I just said that it is not guaranteed, but since there is some kind of tendency towards margin maximization, we can ask what are the implications of such margin maximization. A second possible approach would be to try to prove for some specific settings that gradient flow actually maximizes the margin, and then to use this margin maximization property. And a third possible approach would be just to use the KKT conditions, just to use the equations that specify the KKT conditions. And if we follow this third approach, we don't need any further assumptions because gradient flow is guaranteed to satisfy these conditions. And in this talk, in all three parts of this talk, we'll follow the third approach. So we will only use the equations of the KKT conditions. Okay, let's start with the first paper about generalization in univariate networks. In this part, we consider a model, which is a two-layer ReLU network, where the dimension of the input is 1, so the input is univariate. And we denote here the weights of the hidden layer by Wj. We have bias terms denoted by Bj, and we denote the weights of the output layer by Vj. And we have ReLU activation. And we will assume that the data is such that the labels correspond to some teacher network, which we will denote by n star. So for each training example xi, yi, we have that yi equals to the sign of n star of xi. And we will assume that this teacher network is also a two-layer ReLU network, and we will denote the width of this teacher network by r. Okay, so this is the setting for this part. And for this setting, we show two main results. First, we will show that we can characterize the implicit bias by showing that gradient flow minimizes the number of linear regions. Note that we consider univariate ReLU networks, and such networks compute a piecewise linear function. So we can consider the number of linear regions in this function, and we show that we have implicit bias toward minimizing the number of linear regions. And then we will conclude that this implicit bias implies that gradient flow does not overfit the training data. Then we will also consider optimization, because gradient flow might get stuck in a bad local minimum, and then it will not be able to reach small training loss. But we show that in this case, for random initialization, gradient flow converges with high probability to a small training loss. And then we can combine this optimization result with the implicit bias result in order to conclude that gradient flow converges to a small training loss, and also it minimizes the number of linear regions, and then we can conclude that it, with high probability, it converges to a solution that generalizes well. So this is the high-level result, and now we will talk a bit more about the details. So for the implicit bias part, we show that if gradient flow reaches some sufficiently small training loss after some finite time, then it converges to zero training loss, and it converges in direction to a network with at most O of R linear regions. Recall that R here, R denotes the width of the teacher network. So this theorem says that if gradient flow reaches a small training loss, if it does not get stuck in a bad local minimum of the training loss, then it converges to a solution where the number of linear regions is optimal up to a constant factor. Since the teacher network is of width R, then the number of linear regions of the teacher network can be roughly R. So if we since we are guaranteed to have O of R linear regions in the trained network, then it means that we minimize the number of linear regions up to a constant factor. Now, note that we consider the convergence in direction. And as I said, typically when we train a network with the logistic loss, the scale of the parameters will go to infinity. But since we consider homogeneous networks, then we will only care about the direction of the parameters and not about the scale of the parameters. Because the scale of the parameters only affects the scale of the output, and it does not affect the sign of the output. So when we consider generalization, we only care about the direction of the parameters. And also, the scale does not affect the shape of the function, so it does not affect the number of linear regions. So also our implicit bias result about the number of linear regions is not affected by the scale of the parameters. So since we have this result on the implicit bias, and the result on the implicit bias is independent of the size of the training data set, because it guarantees convergence to a network with O of R linear regions, even if the data set is very large, then we can use standard VC dimension arguments in order to conclude that if the training data set is sufficiently large, we converge to a network that generalizes well. So the implicit bias implies generalization. And since this result does not depend on the width of the network, then it means that even if we train a very wide network, even if the trained network is highly over-parameterized, still gradient flow will not overfit, and it will converge to a network that generalizes well. Okay, so this was the result in the implicit bias. And regarding the optimization result, we show under some assumptions that I will discuss in a moment, that with high probability over the initialization and over the choice of the training data set, there exists some finite time where gradient flow attains some small training loss. So this optimization result says that under some assumptions, if we initialize the weights from some random initialization, then with high probability, we converge to a small training loss. And the assumptions here are mostly mild, except for one assumption, which is that we assume that the scale of the random initialization in the first layer is very large, and the scale in the second layer is small. So the variance of the random initialization in the first layer is larger than the standard initialization that people usually use. And the variance in the second layer, in the output layer, is smaller than what people usually use. We need this assumption for technical reasons in order to obtain this result. And then if we combine this optimization result with the implicit bias result, we conclude that starting from a random initialization with our probability, we converge to a network that has a small number of linear regions, and it also generalizes well. So we have a learning guarantee for this case of univariate networks. Okay. We will now move to the second part, in which we will discuss generalization and adversarial robustness in a setting where the data is clustered. Here we consider also two-layer Rayleigh networks. Again, we denote the weights of the hidden layer by Wj. We have Bass term denoted by Bj, and we denote the weights of the output layer by Vj. And we assume that the data consists of k clusters. So it's a mixture of Gaussians. And we denote the mean of the jth cluster by mu j. And then a random example is drawn by choosing a random index j between 1 and k, and then choosing x from the Gaussian distribution with mean mu j and covariance sigma squared I. And the label corresponds to the cluster. So for each cluster, for cluster j, we have some yj, which is the label that corresponds to the cluster. And then all the examples from cluster j will have the label yj. So it's a very simple setting of clustered data. And we will have some assumptions on the parameters in this setting. First, we will assume that the size of mu j is square root d. It corresponds to the case where each coordinate is of size O of 1. Also, we will assume that sigma is between 0 and 1. Note that if sigma equals 1, then the radius of each cluster is roughly square root d. So if we think about the case where sigma equals 1, then the radius of each cluster roughly is roughly similar to the size of the cluster mean. And finally, we also have an assumption about the near orthogonality of the clusters. This assumption is given by this inequality, which is stated here in the bottom. And it says that the correlations between the cluster means cannot be too large. And also the number of clusters cannot be too large. So for example, if we think about the cluster means as being random vectors on the sphere of radius square root d, then in this case, the correlations between clusters will be roughly square root d, and we will be able to have at most square root d clusters. So if we think about the cluster means as being random vectors on the sphere, then you can have at most k equals square root d cluster. On the other hand, if we want to consider the case where the number of clusters is only a constant, then the restriction on the correlation between the clusters will be much more mild. Okay. Okay, so for this setting, we have this theorem about generalization. Suppose that the number n of examples is larger than the number of k of clusters. So we assume that n is omega of k, and in this talk I will ignore log factors. So up to log factors, we need that n is omega of k. And then we show that with high probability over the training data set, if gradient flow reaches some sufficiently small training loss after some finite time, then it converges to zero training loss and converges in direction to a network that generalizes well on test data. So the theorem says that assuming that gradient flow does not get stuck in some bad local minimum of the training loss, then it must converge to a network that generalizes well. And again, this result is independent of the network width, which means that even if the network is highly overparameterized, gradient flow cannot overfit in this setting, and it is guaranteed to generalize well, assuming that it converges to a small training loss. Also, note that our assumption on the side of the training data set is that we need more examples than clusters. And this assumption is optimal because we cannot hope to generalize well if we don't see at least one example from each cluster. So the sample complexity in this generalization result is optimal up to log factors. Now, regarding the proof approach in this case, the proof here is slightly different from the result on the univariate networks. In the univariate networks result, we showed that there is an implicit bias towards minimizing the number of linear regions. And then we used this result in order, we combine this result with some VC dimension arguments in order to obtain generalization. In this part, we have a more direct proof. Basically, we show that every network that satisfies the KKT conditions of the max margin problem is such that if we choose a random example, then it is classified correctly. So the proof here does not go through uniform convergence or VC dimension arguments. Instead, we just show more directly that given a random example, every network that satisfies this set of equations of the KKT conditions must, without probability, it classifies correctly the test example. Okay, so this was the generalization result. And in the setting of clustered data, we also consider adversarial robustness. Recall that an adversarial example for a given input and a given trained model is a small perturbation, such that if we add this small perturbation to the input, we get a new input, which is very close to the original one, and it looks to humans like the original one, but it is classified differently by the network. For example, we can have an image of a duck, and then we can add a small perturbation, which looks like a random noise, and we will get a new input, which still looks like a duck, but now it is classified by the network as a horse. And it is well known that neural networks in practice are highly susceptible to such adversarial examples, but it is not well understood from the theoretical point of view why neural networks are so susceptible to such examples. And we will try to understand why this is the case for this case of clustered data that we consider here. So in order to understand the bias towards non-robust solutions, we will show two results. First, we will show that in our setting, there exists a robust network that classifies the data correctly. And then we will show that although there exists a robust network, gradient flow will not converge to such a network. We'll show that the implicit bias prevents gradient flow from converging to robust solutions in this case. So let's start with the first theorem. We show that there exists a two-layer ReLU network such that with high probability, if we choose a test example, then this test example is classified correctly by the network, and flipping the sign of the output requires a perturbation of size omega of square root d. Now, in our setting, the size of each example is O of square root d. So it is clear that we can move from a positive cluster to a negative cluster with a perturbation of size square root d. So we cannot hope in our setting to have an adversarial perturbation of size larger than square root d. So the best that we can hope for in terms of robustness is to require perturbations of size omega of square root d. And indeed, this is what we show in this theorem. So the theorem says that there exists a network that generalizes well for this distribution, and it is also robust. Now, the second theorem says that will not converge to such a robust solutions. Formally, it says that if the number of examples is larger than the number of clusters, then with high probability over the training data set, for every two-layer network that gradient flow might converge to, basically we show for every KKT point of the max margin problem, with our probability, if we choose a test example, then we can flip the sign of the output with a perturbation of size O of square root D over K. So the theorem says that
so there's a question from the audience.
Yeah.
Mm-hmm. Yeah, go ahead.
Hi. Yeah, I'm really interested in here the robust and non-robust neural network setting, and my question is that since previously you have introduced the KT conditions, right? The first condition, condition is that the neural network weights can be decomposed into the linear of the gradient of every of every training examples, and the second is that they have the margin that bigger than one over all the training sample, and the third condition is that the interplay between the first two conditions. So I just wondering that here, because the robust network clearly not aligning to the KT sets of the max margin problem of the neural networks, because the neural network you contrasted in the robust, which is robust, is robust, but the gradient flow will convert to a non-robust network. So I'm just wondering that for the robust network you constructed, which condition it varies so that it's not KT points.
Yeah. Okay. So first, the existence of a robust network also gives one example for a robust network, and there are many possible examples. So this is one thing that we should remember. Regarding what conditions are violated, okay, so clearly this network classifies the data correctly, so it satisfies the primal feasibility condition. So it satisfies the constraints of the optimization problem. Now the other conditions are like, it's difficult to separate between the other conditions, because they said that there exists lambda 1 to lambda n such that a few equations such that we have the stationarity condition, and we have the lambda i's are 0 if the point is not on the margin, and so on. So it's difficult to separate between the other conditions because they are combined by these lambdas. So I can just say that there is this network does not satisfy the conditions together, but I cannot say, I cannot point at one condition which is not satisfied.
Oh, I see.
Does it make sense?
Yes. So there are actually, oh, okay, I see. Yeah, may I ask another very quick question about because it is still about this slide. So because here you mentioned that the depth 2 real network actually will convert to a no robust network. I'm wondering, for example, for the leaky neural network, will it become the robust one?
If we consider, you're asking whether if we train a leaky ReLU, whether it will be robust?
Yes.
Okay, so in this work, we don't consider leaky Rayleigh networks. So I actually don't know. I will need to think about it. My guess is that it will also be non-robust.
Okay.
This is my guess,
Thank you very
but
much.
I will need to think about it.
Thank you.
Okay. In the third part of this talk, I will discuss leaky Rayleigh networks, but then the setting will be slightly different. Okay, so the result about non-robustness says that for every KKT point, namely every network that gradient flow might actually converge to, such a network, in such a network, we can flip the sign of the output for a test example with a perturbation of size square root of d over k. So if k, if the number of clusters is larger than a constant, then the size of the perturbation will be non-optimal. For example, if we suppose that the correlations between the cluster means are square root d, and suppose that sigma equals 1, namely the radius of each cluster is also roughly square root d, and suppose that the number of clusters k is also square root d, then, as I mentioned before, this choice of parameters will satisfy our requirements on the near orthogonality of the cluster, and then so it satisfies the requirements for our setting. And then the theorem implies that we can flip the sign of the output with a perturbation of size square root of d over k, which is in this case roughly d to the 1 over 4, which is much smaller than square root d. So in this case, we will have an adversarial perturbation, which is much smaller than what we can hope for in other networks that classify correctly the data. And recall that the case where the correlations between cluster means is roughly square root d corresponds to the case where we think about the cluster means as random vectors on the sphere of radius square root d. Okay. And also, as I discussed in the case of generalization, also when we consider robustness, we only care about the direction of the parameters and not about the scale, because the scale of the parameters only changes the scale of the output because the network is homogeneous, and it does not change the sign of the output. So if for a given model and a given input, we have some adversarial example, some adversarial perturbation, then the same perturbation will still change the sign of the output, even if we change the scale of the parameters. And therefore, considering convergence in direction is good enough for us in order to discuss adversarial robustness. And also, similarly to the previous results that I discussed, this result is also width independent. So it means that we cannot hope to get a robust network by choosing an appropriate width for the trained network. And also, I want to quickly compare this result to a previous result in a paper that I wrote with Gilad Yehudi and Oad Shamir. In the previous paper, we considered a case where the training data set is nearly orthogonal. So basically, we assume that all training examples are nearly orthogonal. And in this case, we showed that there is implicit bias towards non-robust solutions. But there are two main differences between the previous work and the current work. In the previous work, we considered robustness with respect to training data. So we showed that for every training example, we will be able to flip the sign of the output with a small perturbation. And in this new result, we consider robustness with respect to test data, which is a more common notion for robustness. Because we showed that for a test data, without probability, we will be able to flip the output with a small perturbation. So this is one difference. And the second difference is that since in the previous work, we assumed that the training data set is nearly orthogonal, it implies that we can allow the number of examples must be smaller than the dimension in the previous work. So we had this strong assumption about the size of the training data set. And in the new work, we only assume that the cluster means are nearly orthogonal. And in our case, the number in the new result, the number of examples can be much larger than the input dimension. So these are the two main differences. And I will also mention that our non-robustness proof relies on ideas from the previous work.
May I ask a question?
Yeah, sure.
Can you go to the previous slide? In this theorem, you actually assume that the data distribution is a clustered one, right?
Yes.
Yeah. So I'm wondering whether this theorem holds when you consider other distributions.
So we only proved it for this setting. I suppose that there might be other settings which will have the same property, but I can't give a more general characterization for a setting that will satisfy this property.
Yeah.
I mean, basically, if you consider non-robustness, you want a setting where the positive inputs and the negative inputs are separated. So considering a cluster setting where the clusters are sufficiently far away from each other, it seems like a natural setting for studying robustness. But you can consider many other settings.
For example, in your another paper about binary overfitting, you actually consider another distribution called
right.
subgaussian marginal. So how about this distribution?
Yeah, it's a good question. In the other paper, basically the subgaussian distribution, yeah, so we can think about the size of each of the signal as being d to the row for some row between quarter and half. So the distance between positive and negative results will be roughly at in this order. And then, yeah, you can ask whether what would be the size of the perturbation, whether it is much smaller than the distance between the positive and negative results or not. I actually didn't try to think about it in this setting because I felt that this cluster setting that I'm discussing in this work seems like the assumptions on this setting are weaker than the assumptions that we needed to use in the case of benign overfitting. So I felt that it is more natural to consider non-robustness under the weaker conditions than consider the same question under the strong assumptions that we needed in order to show benign overfitting.
Thank you.
Okay, so to conclude the results on this cluster setting, we showed that the implicit bias implies generalization, but it also implies non-robustness. So there is an advantage and a disadvantage for this implicit bias. Okay, now let's move to benign overfitting. So we consider benign overfitting in leaky-ReLU networks and linear classifiers. We say that there is benign overfitting if a learned predictor, on the one hand, interpolates noisy training data, and on the other hand, it also generalizes well on test data. Note that here, when we talk about benign overfitting, we consider noisy training data, which means that we have label noise. And recall that in the previous settings that we considered, we didn't have label noise. And in general, showing generalization in a setting where we have label noise is more challenging if we consider interpolating solutions. And the notion of benign overfitting started from empirical results showed by Zhang et al. They showed that when they trained neural networks, over-parameterized neural networks on noisy training data, they interpolated the noisy training data, but still generalized well. And this observation was very surprising. And since then, there have been a huge number of theoretical works that tried to understand under what conditions, under what assumptions on the setting, such a phenomenon can occur. Intuitively, we can think about benign overfitting with the following illustration. Suppose that we have inputs which are real numbers, and the labels are also real numbers. And suppose that the labels correspond to a linear predictor, but we also have some label noise. So the labels are roughly correspond to this linear predictor with some additional noise. And in this case, this linear predictor is the base optimal predictor. And if we train an over-parameterized model to interpolate the training data, we might get harmful overfitting, which means that we will interpolate the training data, but we will not generalize well. And we can also get benign overfitting, which can be illustrated by this cartoon. It's not an actual model that I trained. It is just an illustration to give some intuition about the notion of benign overfitting. So what we see here is that we interpolate the training data, but for most inputs, this predictor behaves similarly to the base optimal. So if we choose a random test example with high probability, the model will behave similarly to the base optimal, but it still interpolates the noisy training data. So this is a more like an intuition for the notion of benign overfitting. And one of the main reasons that benign overfitting is challenging is because we cannot easily use the tool of uniform convergence in order to prove generalization. Recall that uniform convergence is a classical approach to prove generalization. It means that if we consider some hypothesis class H, then the uniform convergence property means that if we have a sufficiently large training data set, then for every hypothesis in the class, the training loss will be close to the expected test loss. So for every hypothesis in the class, the behavior of the hypothesis on the training data will be similar to its behavior on test data, which means that in a sense, what we see is what we get, because if a predictor is good on the training data, then it is indeed a good predictor. And if it is bad on the training data, then it is really a bad predictor. And so if we have this uniform convergence property, we can just choose one hypothesis from the class, which behaves well on the training data. And this approach is called empirical risk minimization. For example, in the part on univariate networks, we showed that there is implicit bias towards minimizing the number of linear regions. And then we used uniform convergence arguments on this class of functions with a small number of linear regions in order to obtain generalization. So we combined implicit bias and uniform convergence. However, if we consider a benign overfitting setting where we have label noise, then such a result cannot be easily shown, because suppose that we consider classification and we have some label flipping noise. suppose that we flip each label with some probability eta, which is some constant larger than 0. Then for such a setting, the test error is at least eta. For every predictor, we cannot get test error, which is smaller than eta. However, if we interpolate the training data, then the training error will be 0. So it means that there must be a gap of at least eta between the training error and the test error. We cannot hope to show that if the size of the training data set goes to infinity, then the gap between the training error and the test error goes to 0, because it cannot be the case. And therefore, showing generalization using uniform convergence becomes much more challenging. So this is a reason that binary overfitting is usually challenging. Now, in this work, we consider leaky Rayleigh networks and linear classifiers. And we show binary overfitting for both models under some assumptions on the distribution. The result on leaky Rayleigh is the first binary overfitting result for fully connected leaky Rayleigh networks. And it is worth mentioning that there is a prior work by Frey et al. That considered binary overfitting in smooth leaky Rayleigh networks, namely in some smooth version of leaky Rayleigh. And the setting in this previous work is more specific in the sense that the assumptions on the distribution, the distributional setting is essentially a special case of the setting that we will consider in this work. Also, there are two other previous works, and I believe that some of the authors of these works are in the audience. And these works considered binary overfitting in nonlinear convolutional networks. But except for these papers that I just mentioned, all other papers on binary overfitting considered linear predictors or kernel regression. So these are the only works on nonlinear networks. Also, our distributional settings that I will discuss in the next slides are different than the settings that were considered in previous works. And our proof technique relies on the KKT conditions of the max margin problem, and previous works showed binary overfitting with different techniques. So we consider two distributional settings. The first setting is a sub-Gaussian setting, and the second is a clustered setting, which is sort of similar to the previous part, but the technical assumptions are not exactly similar. And as I said, we consider two types of models. We consider linear classifiers and two-layer leaky Rayleigh networks, where a two-layer leaky Rayleigh network is given by this expression, where the activation phi is the leaky Rayleigh function, namely phi of q is the maximum between q and gamma q for some constant gamma between 0 and 1. Now, I will briefly discuss our distributional settings. I will not give all the technical details about our assumptions, and instead I will give a high-level description for each setting, and then I will give one example for each setting. So in the sub-Gaussian setting, the inputs are such that each coordinate is independent mean-zero sub-Gaussian, and the label are determined according to the first coordinate. So we can think about the first coordinate as the signal, and then the label is the sign of x1, but it is flipped with some probability eta. So y equals to the sign of x1 with probability 1 minus eta, and it equals to minus the sign of x1 with probability eta. And we assume that the variance of x1 is sufficiently large and also that the covariance matrix has a sufficiently high rank. And for example, we can think about the case where the input X is drawn from a Gaussian distribution with mean 0, and covariance matrix such that the variance of the first coordinate, which is the signal, is d to the rho, where rho is a constant between half and 1, and the variance of the other d-1 coordinates is 1. And for this distributional setting, we show benign overfitting, and we can tolerate noise ratio eta, which is any constant smaller than half in the case of linear classifiers, and any constant smaller than half times gamma squared, where gamma is the leaky ReLU constant in the case of leaky ReLU networks. Okay, so this is the sub-Gaussian setting. And in the clustered setting, the cluster setting is sort of similar to what we already discussed. We have k nearly orthogonal clusters. We have label flipping noise eta. So it means that each label is determined by the cluster, but it is flipped with some probability eta. And we also have some additional assumptions on the scale and the correlations between clusters, and these additional assumptions are different from our assumptions in the clustered setting that I discussed in the previous part of this talk. And again, I will not give the formal assumptions. Here, I specify one choice of parameters that satisfies our assumptions. So if we have k clusters and mu q is the mean of cluster q, then we choose x from the Gaussian distribution with mean mu q and covariance matrix I. And then I specify here some possible values for the sizes of the cluster means, the correlations between the cluster means, the number of samples and the number of clusters, such that if we choose these values, then it will satisfy our technical assumptions for the clustered setting. And here we also tolerate noise of at most of any constant smaller than half in the case of linear classifiers, and any constant smaller than half times gamma squared for leaky ReLU networks. Okay. Which time do I have?
Yeah,
Okay.
yeah, you have a maybe 5 more minutes. Yeah, I think you have enough time.
I have 10 more minutes?
5 more minutes.
5 more? Okay.
Yeah.
Okay, so for the settings that I just described, we show that with our probability over the training data set, gradient flow exhibits benign overfitting, which means that it interprets the training data and achieves test error of which is close to eta. So the test error is close to the base optimal test error. Now, the proof approach, as I said, relies on the KKT conditions of the max margin problem. Basically, we show that every KKT point in our settings has a linear decision boundary. Now, of course, in the case of linear classifiers, it is obvious then that the decision boundary is linear, but in the case of leaky ReLU networks, these networks compute nonlinear functions, but still we show that the decision boundary is linear. So it corresponds to some linear classifier. And this linear classifier is not the max margin classifier, but it has this nice structure that it can be expressed by a weighted sum of training examples, where the weights in this weighted sum are approximately balanced, which means that the ratio between the maximal weight and the minimal weight can be bounded by a constant. So we have this nice structure, nice property on the linear classifier that corresponds to the decision boundary. And then we show that in our settings, every classifier, every linear classifier with these nice properties generalizes well. And therefore, we obtain benign overfitting. Okay, if I have, I can try to give a little bit more intuition, but maybe if you have more questions, then maybe it's a good time for questions, and otherwise I will describe this intuition. Okay, so let's consider the case where we have two opposite clusters. One cluster has min mu and labels +1, and the opposite cluster has min minus mu and labels -1. And in the mu cluster, each example is of the form mu plus z, where z is a standard Gaussian, and similarly for the opposite, the minus mu cluster. And also suppose that we have label flipping noise of eta. So for this case of opposite clusters, let's first consider the linear predictor, which is given by the sum of the examples. So let mu hat be the predictor, which is the sum of yi xi, where xi yi is the ith example in the training data set. This predictor, this sum can be written as two sums, one over the clean examples and another over the noisy examples. And then we can easily obtain that we can write this mu hat predictor as a sum of two terms. The first is in the direction of mu, and it corresponds to the signal. And the second term is a sum of over the zi's, which are the deviations from the cluster means of the training examples. So for this mu hat predictor, if the size of mu, the size of the signal is too small, then it will not generalize well on test data. So in order to generalize well, we need the signal to be sufficiently large. But we can also see that if mu is too large, then this mu hat predictor will not interpolate noisy training data. Now, of course, the gradient flow will not converge to mu hat, and it will converge to some solution, which is a KKT point of the max margin problem. Now, by definition, every KKT point interpolates the training data. So in order to show that the KKT point exhibits benign overfitting, we need to show that it also generalizes well. And we show that if the size of mu is not too large, then every KKT point has a linear decision boundary that corresponds to a linear classifier, which is an approximately balanced weighted sum of training examples. So if the size of mu is not too large, then every KKT point behaves roughly like this mu hat predictor that we discussed previously. And then similarly to this mu hat predictor, if we also assume that the size of mu is not too small, namely if the signal is sufficiently large, then this approximately balanced linear predictor generalizes well. So overall, we get that if the size of mu is not too large and not too small, then every KKT point corresponds to a linear predictor with this nice structure that generalizes well. And therefore, we conclude that there is benign overfitting. Okay, I will conclude. So as we said, the implicit bias seems to be a key factor for understanding generalization in deep learning. And of course, understanding generalization is a fundamental question in the theory of deep learning. And in this talk, we discussed 3 different settings where we can use the characterization of the implicit bias in order to prove generalization. But of course, the path towards understanding generalization in more realistic and complex models is still very long, and there is still a lot of work to do in this direction. Thank you.
Yeah, thank you. Thank you for the great talk. Yeah, let's take some questions from the audience. So we already have 2 questions during the talk, but let's see if we have more questions from the audience. So if you have a question, you can raise your hand. Oh, okay. So we have 2 questions from the audience. Let's see. Oh, here. Yeah, go ahead. You can unmute your. Yeah.
Hi, can you hear me?
Yeah, we can hear
Yes.
you.
So for your third result, I see that the result only holds for leaky ReLU. So so for the part of ReLU, does it is it due to some technical difficulties, or the result does not hold at all for ReLU?
Yeah. So the main reason that we discussed leaky ReLU is that in leaky ReLU, the decision boundary of the KKT point is indeed a linear classifier, which makes it easier to analyze. In the case of ReLU, it will not be a linear classifier. It will still have some nice properties, which might be useful in order to show benign overfitting. But in this work, we wanted to consider this small, simple setting where the decision boundary is linear. Yeah, so it is possible that the same result also holds in ReLU networks.
Okay, thank you.
Yeah, yes, another question from Tamaya. So let me allow you. Yeah, you can unmute yourself and ask question. Hi, Tamaya, you can unmute yourself. We cannot hear you. You need to unmute yourself. Okay, so when we are waiting for Tamaya to unmute herself, that I have a question. So in the last part, you are saying that the signal cannot be too large or cannot be too small. But in my previous paper on this benign overfitting in 2-layer convolutional neural network, actually, there's a phase transition in terms of signal noise ratio, and in our sighting, the larger the signal strength actually does not prevent, is not preventing
Right.
benign overfitting. So I wonder, do you have any intuitive reason why in your sighting the signal noise ratio need to be in this bounded?
Yeah, so this is basically an artifact of the analysis. So I'm not saying that if the signal is too strong, we will not have benign overfitting. What I'm saying is that if it is too strong, then the KKT point will not have this nice property that we need in order to prove benign overfitting. Right, so it is still possible that we will have benign overfitting, although the KKT point will not correspond to a linear classifier.
Oh,
so we might still have benign overfitting even if the signal is very strong. This is what I'm saying. It's not. I'm not showing a negative result for large signal. I'm just saying that our analysis will not go through in this case.
Okay, I see. All right. Yeah. So, any other questions from the audience? Okay. So, in the interest of time, if there's no more questions, let's thank Vardi again for his great talk. Thank you, Gal, and yeah, hope to see you in person. Yeah, sometime in some conferences. Thank you for sharing.
Thank you very much.
Thank you.
Bye.
Bye.